In this work, we present AugMix, a simple yet surprisingly effective training routine which consists of a new data augmentation procedure and a consistency loss term. In our experiments, we find that AugMix improves the robustness and uncertainty of deep computer vision models. We measure our method's robustness to image corruptions, as well as uncertainty calibration on the CFAR-C and ImageNet-C benchmarks. These two datasets apply 15 corruptions, shown here, across varying severity levels to the CFAR and ImageNet test sets. Our data augmentation procedure uses 9 operations from AutoAugment, which do not appear in the common corruptions. Data augmentation is an important component of training deep neural networks, without which high-capacity models can experience overfitting and low testing accuracy. We extend this basic concept and introduce a new procedure which augments a clean image in multiple branches of different depths by composing basic image transformations. These branch outputs are then mixed with each other and then with the original clean image. In each instance, we randomly sample the operations, the intensity, the depth of each branch, and all mixing weights. We apply our procedure on top of the standard ResNet data augmentation of random cropping, resizing, and flipping. In order to evaluate corruption error fairly, we avoid operations which appear in the ImageNet-C corruptions, but would suggest including these for general use. Here, we show an example of our procedure alongside some existing data augmentation methods. During training time, we augment each image twice and compute the Jensen-Shannon divergence between the model's predictions of the clean image and both applications of our augmentation. The Jensen-Shannon divergence term is added to a standard cross-entropy loss computed only on the clean image to form our loss function. Intuitively, the consistency loss encourages the model to learn invariant representations across diverse augmentations of the same image. In our experiments, we find that AugMix cuts the average error on CFAR-10C down by half from the previous best. This marks a significant step towards optimal performance on CFAR-10C, as estimated by a model's error rate on the clean test set. We also evaluated the performance of AugMix on ImageNet-C with a ResNet 50 model. The measure of interest here is mean corruption error, which is an average of the error rate of each corruption, first normalized by AlexNet performance. We find that AugMix improves both clean accuracy and mean corruption error for ResNet 50 on ImageNet-C. Additionally, we find that AugMix can be composed with orthogonal approaches such as stylized ImageNet for even further robustness gains. While it is to be expected that model error increases in response to more severe corruptions, it might be hoped that we could rely on the model's confidence scores to discard likely incorrect classifications. Unfortunately, it has been observed that deep neural networks are prone to miscalibrated predictions on out-of-distribution data. We say a model is perfectly calibrated if it is 90% accurate across predictions for which it gives a 90% confidence score, and so on for all confidence scores. The root mean squared calibration error measures how far a model is from being perfectly calibrated. In our own experiments, we find that a standard ResNet 50 model, even when ensembled, produces increasingly miscalibrated predictions on more severe corruptions. However, when trained with AugMix, the same model achieves significantly lower calibration error at all severities. Even more exciting is our finding that training a 3-model ensemble with AugMix entirely mitigates the impact of ImageNet-C corruptions on uncertainty calibration. Finally, we present our findings on 2 prediction stability benchmarks, CFAR-P and ImageNet-P. CFAR-P and ImageNet-P sequentially perturb each test image. The measure of interest here is mean flip rate, or MFR, which is an average of top 1 flip probability, first normalized by AlexNet performance. AugMix also drastically improves prediction stability by 60% on CFAR-P and by 20% on ImageNet-P. To conclude, AugMix is a simple yet surprisingly effective data augmentation and regularization technique which significantly improves accuracy and uncertainty under dataset shift. For more details, please see our full paper and code repo or stop by our virtual poster session on Monday and Tuesday, April 27th and 28th from 9 p.m. to 11 p.m. Pacific Time. Thank you.